Welcome back, math lovers and math contest enthusiasts. We're going to be continuing on with our look at the 2012, my mistake, the 2012 Csmc paper. The video should be clearly marked, so I do apologize. It's the 2012 senior paper. Okay, we already did question 1 in the B part, that's the written portion. So let's take a look at question number 2 without delay. So consider the equation x squared minus 2y squared equals 1. Now, actually, this type of equation is called a Pell equation. They have a long and interesting history, so I might do a video on those. And that does mean that I have a little insight into this problem already. But we'll try and approach it from a newbie's perspective. So this equation we label 1. There are many pairs of positive integers x and y that satisfy equation 1. In fact, there are going to be infinitely many. That's neither here nor there. A part. Determine a pair of positive integers x and y with x less than 5 that satisfies equation 1. Okay. So there's not a lot of approach as to how best to solve this. What we need to do is, we know that they're going to have to be positive integers, and x is less than 5, so we could really just try x equals 1, what would y have to be? X equals 2, what would y have to be? Until we get a final solution. If you wanted to, you could look further in the problem. I already see a solution, 3 plus 2, so taking y is equal to 2 and x equal to 3 will probably be a solution. But let's do it the way you would likely approach the problem. We're asked positive integers, and x is less than or equal to 5. That means there's only 5 possibilities for x. We can just try each of them in turn and solve the equation for y. So we get ourselves a brand new page. Now we're just asked for one pair. So once we find one, we can stop. So we have 1 squared minus 2y squared equals 1. So that tells me that 0 is going to be equal to 2y squared. And that tells me that y is going to be equal to 0. That doesn't work. We want y to be a positive integer. How about we try x equals 2? So that tells me 2 squared minus 2y squared equals 1. I can already tell this isn't going to work because we have an even minus an even equals 1. But we rearrange. We bring the minus 2y squared over to this side. This is a 4. We bring the 1 over to this side. So at that point, y is going to be the square root of 3 over 2. So that also does not work. It's positive, sure, but it's not an integer. So 3 squared minus 2y squared equals 1. So we rearrange, we get 9 minus 1, which is 8, equals 2y squared. So y squared is equal to 4, and that implies that y is equal to 2. Or minus 2, but we're really only looking for positive values of y. So it satisfies the equation that they have labeled 1. Okay, 3 and 2, and I believe I called that. Looking ahead in the question would give us sort of a bit of a hint as to the numbers we should be using, although they're being expressed other than just solving this equation. Anyway, this whole thing has to do with Pell's equations and quadratic number domains, which is something that if you're curious about, you can look up, but by no means will it be easy. This is a grade 11, 12 contest. Quadratic domains are sort of ring theory, which is more advanced university stuff. But it's always nice to see that there's places you can go with these contest questions. There's real theory behind them, and so someday you guys might encounter the real theory behind this question. B part. Determine a pair of positive integers, u and v, such that 3 plus 2 root 2 all squared is equal to u plus v root 2. Show that uv satisfies equation 1. Okay. So we're going to need to expand this out and collect the terms that are all integers and collect all the terms that are in terms that have a root 2 in them. And we should be able to simplify and get positive integers u and v. And then we just need to plug them into this equation and show that it is indeed satisfied. So that's going to be 3 plus 2 root 2, 3 plus 2 root 2. So we can use our favorite FOIL technique or George if we want to. So a very nice guy. Here's his hair, here's his nose, here's his chin. This is George, but it's just another way of doing FOIL, which is do the firsts, do the outsides, do the inner ones, and then do the lasts. Either way, we get 3 times 3 plus 3 times 2 root 2 plus 3 times 2 root 2 plus 2 root 2 times 2 root 2. So we can simplify that. That's 9 plus 6 root 2 plus 6 root 2 plus, okay, so 2 times 2, that's 4. Root 2 times root 2, that's another 2, so that's 8. Simplifying even further, we have 17 plus 12 root 2. So we take u and v to be 17 and 12. And we check that they satisfy that equation number 1. So 17 squared minus 2 times 12 squared, that's 281, 144. You can get your calculator out if you're not familiar with these squares. But hopefully if you've been doing enough of these contests, you should be. So 289 minus 2 times 144, we can check that out on our calculator. And we get 288. So it's exactly 1. 289 minus 288, that's going to be 1. So they do satisfy equation 1, which is exactly what we were asked to show with u and v once we got them. Okay. C. Suppose that AB is a pair of positive integers that satisfies equation 1. Suppose that C is a pair of positive integers such that it satisfies this expression. So A plus B root 2 times 3 plus 2 root 2 equals C plus D root 2. Show that CD satisfies equation 1. Okay. So AB can really be anything. So what we should do is exactly what we did in the last case, which is just expand this out, but instead of 17 and 12, we'll get something in terms of A's and B's for our two values of C and D. And then we just need to show that they satisfy equation number 1. Okay. So we have A plus B root 2 3 plus 2 root 2. So we can use our favorite FOIL technique, and we can get 3a plus a2 root 2 plus 3b root 2 plus b root 2, 2 root 2. So that's 3a plus 2a root 2. We're just changing it so the one constant is in front. And then 2 times b, that's 2b. And then root 2 times root 2, that's 2. So that's going to be 4b. Three a plus 4b, and then we have 2a plus 3b root 2. Okay, so C and D, we now have expressions for those guys. And we were asked to show that C and D satisfy the original equation. So we plug them in. 3a plus 4b squared minus 2a plus 3b squared. Okay. So we can expand these out using FOIL, or if we just know the formula for a sum being squared, we can use that. We'll get 9a squared plus 2 times 3 times 4, so that's going to be 24ab plus 16b squared. We're going to subtract off 4a squared. Uh, 12ab, and then 9b squared. So that amounts to 5a squared plus 12ab plus 7b squared. Okay. So we have a 5 here, we have a 7 here. 5 plus 7 is 12, and I'm betting that's no coincidence. So what if we were to split up this 12ab into 5ab plus 7ab? Alright, well we could take out a factor of 5a from this first little bit, and we get a plus ab. And then we get 7b times a plus, oh sorry, that should be a plus b. And then 7b times a plus b. So now we have a factor of a plus b in each of these. Okay. Still want to show that this is equal to 1. And I'm actually at a bit of a loss as to where to go with this. If I want to show this is equal to 1, I would, and we know that these are going to be integers. So we've got ourselves a bit of a problem here. So maybe simplifying this straight away isn't exactly what we should be going for. Oh, you know what it is? I forgot a 2 here. Okay, good. I was wondering what was going on with this. Because I was getting to a point where a plus b would have to be 1, and then 5a plus 7b would also have to be 1. Okay. And with a and b being positive integers, which we were told, there's no way that that can happen unless... No, actually, there's no way that that can happen. So 9a minus 2 times 4a, so that's just going to be a squared. Minus 2 times 12, that's going to be, well, that's going to be plus 0ab, which we'll get rid of in a moment. 16b squared minus 2 times 9b squared, so that's going to be minus 2b squared. A squared minus 2b squared, which is equal to 1. Now, that's just equation 1 in terms of a and b. So since a and b were told to satisfy equation 1, we know that this value is going to be 1. And we can get rid of this error. So that also satisfies equation 1. Okay, very nice. D, which is the last part of this question, determine a pair of positive integers x and y with y greater than 100 that satisfies equation 1. Okay. So, what have we seen so far in this question that should help us? The last part usually should build on what we've seen before. We got a pair, but that was with x less than or equal to 5. It was very restricted. Here, y can be just about anything. B part, we showed that 3 plus 2 root 2 squared gives us another pair of integers that satisfies equation 1. And in C part, we extended that and showed that not if we start with 3 and 2, which part A told us satisfied equation 1, but if we start with any old pair that satisfy it, we get another pair out, satisfying equation 1. And this C and D that we get out, we have formulas for those. It's 3a plus 4b, and then 2a plus 3b. So those are both going to be bigger than the a and b we put in. I think it was 5 and 7 that we saw, or maybe it was 7. I think it was 7 and 5 actually. No, 17 and 12. So what we can do is use this 12 as A, or sorry, this 12 as B and 17 as A, and use what we saw in part C with these formulas 3A plus 4B and 2A plus 3B to build up bigger solutions where the Y value gets larger. Okay, so 3 times 17 plus 4 times 12 2 times 17 plus 3 times 12. So what's that? That's 51 plus 48. So that's 99. And then we have 34 plus 36, 70. So that also satisfies 1. The y value is still too small, though. But if we were unsure of this, what we could do is we could double check. We could say 99 squared minus 2 times 70 squared. What's that? Well, that's going to be 1. So we can double check that we haven't made an arithmetic mistake here. So 3 times 99 plus 4 times 70 and 2 times 99. So this will definitely be greater than 100. So this will be the last one we'll need to do. 3 times 70. So what's that? 3 times 99 plus 4 times 70. That's 577. And then 2 times 99, well, that's 198. Plus 3 times 70, that's 210, so that's 408. So that also satisfies 1. Again, we can double check our arithmetic by saying 577 squared minus 2 times 408 squared. Well, that's equal to 1, so we do indeed satisfy 1. But now our y value is greater than 100, which is what we want. So 577, 408. It's such a desired x and y pair. Okay? Notice that we explained what we were doing. We saw a formula in part C, and we mentioned that. We mentioned what the formula is, we repeat it, so they know we know what we're talking about. And we took a pair that we already saw, which is B. We saw in B that 1712 satisfies 1. We used that to produce another set of values. Those were too small, so we produced yet another set of values. And those were finally big enough. Because if we double check the question, make sure we answered everything, we need the second value, y, to be greater than 100. And we do indeed have a pair of positive integers, x and y, with y greater than 100 that satisfies 1. So that wraps up all of question 2. For D part, we really used C and we really used B. And that's usually how these questions with multiple parts go. You really, the final question really ties everything together. So I think that was quite nice. And as I said, you can look up Pell's equation, which is what this question is based on. And you'll see that this 2 here, we can change it to anything. We can do x squared minus 3y squared equals 1, and that gives us a whole other set of values. A really cool one, if memory serves, is x squared minus 61y squared equals 1. Took centuries to solve that. I have it in a book by Ian Stewart as well. I think it's Math Hysteria. But yeah, definitely look up Pell's equations, P-E-L equations, and you can find some very interesting math. So it's a good question, good contest question, and something that if you go on in math, you might encounter again with Pell's equations. But thank you all for watching, and I'll see you guys for question number 3 in the very next video.